Swayam Prabha. Digital India. Educated India.
Welcome back to another lecture of this course titled Robust Control, and as promised earlier, over the past few lectures, as with the next few lectures also, we shall be delving into the properties of vector spaces, linear maps, and more specifically from this lecture onwards we shall start to see certain features of matrices which apparently seem to capture these linear maps over vector spaces subject to the choice of a given ordered basis. So in the previous lecture we have seen something that you are familiar with in terms of so-called similarity transformations of matrices is nothing but, when taken in terms of these vector spaces, basically a change of basis, right. So you know that the number of elements in the basis set for a finite dimensional vector space is unique, but the choice of the basis is far from unique, right. There can be an infinite number of choices for the basis, particularly when the field that we are dealing with is either the real numbers or the complex numbers, right. Okay. So now in this lecture we shall start to see some other properties of these linear maps, and we shall see some notions such as invariant subspaces with respect to linear maps, and thereafter we shall look at the manifestation of these linear maps in terms of matrices, and we shall also see what some of these special invariant subspaces lead to when we look at these linear maps as nothing but matrices across Fn. Okay. To be more precise, we shall look at those linear maps that are basically mappings from a vector space V to itself, right, and therefore when we look at their matrix counterparts, their matrix representations, these matrices will be nothing but square matrices, okay. And we shall see how when we say invariant subspaces, the invariant subspaces over the abstract vector space V also lead to invariant subspaces of F to the n, okay. We shall see the connection between the two, and once you are thorough with the idea of coordinate representation subject to an ordered basis, it will turn out that this is not really a big deal, yeah. Although it might look like these are not very well connected at first sight, but again what comes to our rescue is this idea of coordinate representation, okay. So without further ado, let us try to capture what we have seen in the previous lecture. What we have seen is that, well, if you have been given two bases, one let us say V1 through Vn and the other basis being U1 through Un, and then suppose you know how each member of the new basis, that is U, right, that is U1 through Un, so any one of those UKs, how they can be represented in terms of the old basis. Once you know that, it turns out then that is all you need to know. So you see, then you build a matrix, each of whose columns represents, yeah, the representation of members in the new basis in terms of the old, yeah. So as you can see before yourself here, this is new in terms of the old, yeah, and then you get this transformation matrix which you can call as T here, right. These alphas basically give you the representation in terms of the old basis. So a vector that is represented as alpha 1, alpha 2, dot 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 till alpha n in terms of the old basis is nothing but the same as writing this vector as V is equal to excuse me, alpha 1 V1 plus alpha 2 V2 likewise, Yeah, that same vector can also be written in terms of the new basis. Yeah, but what will be the equivalent representation? That can be, it turns out, obtained by just hitting this n tuple of alphas with a T inverse on the left. Yeah, by T inverse I mean the inverse of the T matrix, and we also saw that this T matrix is guaranteed to be invertible, quite simply because after all it is representing the same vector, right. So, it cannot be singular. If it were singular, it would violate the tenets of the basis, that is, the elements of the basis have to be linearly independent. So, we have seen all of this. Now, the question is, so how do you get to represent a linear map? Say we have a linear map from V to itself, in which case it will no longer be called a linear map. I mean, it is still a linear map, but it has got a special name, it is a linear operator. Okay. So, once we have this linear map from V to itself, we call it a linear operator, and it then stands to reason that suppose I have this linear map represented as a matrix in terms of the basis BV, and you have the same linear map represented in terms of another basis B tilde V. So, the question we ask ourselves is, how do we go back and forth between these two? Yeah, what I wonder is the relation between these matrices. We have seen that any arbitrary vector represented in terms of one basis is related to that same vector represented in terms of a new basis by virtue of this matrix T. So, we wonder, how are these linear maps related? Yeah, when you represent this linear map as a matrix in terms of one basis, can we also represent this linear map in terms of another basis by doing some operations on the linear map that we already have? Yeah, that is what we are now going to try and see. So, I am going to just draw a sketch and hopefully you shall see the connection here. So, look, what are we starting with here? We have originally this vector space V, and we have this linear map. So, this is an abstract vector space V, this is the same abstract vector space V, and between these abstract vector spaces we have this linear map. Look, this A, the way I am writing here, later on we will see that interchangeably we will use A with or without the box bracket to represent matrices without exception, but for now this A is not yet a matrix, it is just a linear map, right. Now, what we do is we take every element in this vector space V and subject to a particular basis. Okay. So, suppose you have this let us say this BV, yeah, and you have another basis which is B tilde V, all right, and let us say we take the relation we developed yesterday or in the previous lecture, where we saw that if you take any representation in terms of BV of a vector, then in order to get the representation in terms of B tilde, this is exactly the relation that it turns out is going to be true, all right. So, if you want to go from this V to Fn, f to the n, or if you want to go from this V to this f to the n, yeah, what do you have to do? You have to hit it with some ordered basis and coordinates therefrom, right. You obtain a coordinate of representation of every vector. So, given a particular basis, let us say this BV, yeah, it is like assigning some correspondence between elements in the abstract vector space V and elements in f to the n, and let us say that correspondence is given by E, all right. So, let us say this is the correspondence that you give by E, okay, and this E is related to this choice of this ordered basis BV, yeah. That is pretty straightforward, right. Okay. Now, if we look at this linear map A and its matrix representation, now that we are in f to the n, now it makes sense to talk about this matrix representation, is it not? So, what then do we do here? Let us say we depict that matrix as this, within the box bracket we put it. So, let us say this is the matrix representation of the linear map A in terms of the basis BV, all right. So far so good, right. But now look at this thing that we did the other day. Yeah. What do we have to do in order to go from a representation in terms of BV to a representation in terms of BV tilde? The same vector that originated in this abstract vector space has a representation in terms of Fn in terms of BV, and now we want to represent it in terms of BV tilde. Or rather B tilde V. Yeah. So what do we need to do? We need to hit it with a T inverse, right? Look at this relation here. So if you want this, then you had better hit both of these sides with T inverse. I already have this. So here I had V, here I have V in terms of BV, and here I am trying to get to the representation of V in terms of B tilde V. So I have to hit it with a T inverse, right? And then I get to the same Fn. It's just a change of coordinate or change of basis essentially. Same thing I do here. If I want to get from here to here, I have to hit it with a T inverse, and I get its representation in terms of the new basis B tilde, right. And now the question before me is, how is this map related? So this is what I don't know, okay. This is the question before me. In the earlier case, you remember, I knew one of these, I knew this was easy to get, and knowing these two I can get this. This was initially unknown, but then finally I found that through this relation I can relate them, every vector. Now I am trying to do the same thing with a map. So it turns out now I can forget about this original place from where they originated. This part of the diagram I can now forget about. Yeah. And now I can just focus on the latter part of this diagram that I have before me on the screen. So let me just focus on this part. Okay. Let this be my starting point and this be my end point. So I want to take a vector here. Sorry, yeah, there it goes. Yeah, so I want to take a vector here and map it here, and I want to find out what that representation, the matrix, looks like. So look, if you look at it as a path from here, then I am getting from here to here, whether I follow this path or I follow this path, this is what is called a commutative diagram, right. So whether I go from this Fn, this representation in terms of, sorry, B tilde, yeah. So whether I go for this representation, and this is basically that same thing hit here, right. So this is the representation of the resultant mapped vector in terms of B tilde, right. So if I want to go from here to here, whether I adopt this direct path, that is I use this particular matrix representation in terms of B tilde, or I go along this path, the effect is the same. When I go around this roundabout path, it basically means that I am first mapping this representation in terms of B tilde, getting it back to the representation in terms of BV, and then hitting it with the corresponding matrix which I know to be true, which I have knowledge about, because I know the matrix representation in terms of BV, I do not know the representation in terms of B tilde, right. So I basically go back to this, get the representation of the vector in terms of BV, hit it with the matrix representation in terms of BV, and end up here. And then I can again hit it with this T inverse to get the representation in terms of B tilde. Yeah, fair enough. Now it turns out that instead of all this, if I had this matrix representation in terms of B tilde ready made, I would not have had to go about this roundabout path. Yeah, so these are equivalent. So then it turns out that in the operator theoretic sense, which here turns out to be the matrix representation, I can just write that this red part here that I have marked in this commutative diagram, the direct path here, is tantamount to this whole roundabout path here, which let me mark out in some other color, maybe green. Yeah, so this is the green part of it. Yeah, so this is the green part of it. Okay, let me, yeah. So what is this green part equivalent to? Yeah. So what I have then is, it turns out I am first, if this, in getting from here to here, from top to bottom I have to hit with T inverse, then the reverse path if I have to traverse, I have to hit with a T. So first I operate with a T. Remember, this T is already known to me, I derived what the T is in the last lecture, right. This T is basically a matrix whose columns depict the representation of the new basis, elements of the new basis in terms of the old basis. That is the U's in terms of the V's, elements in B tilde in terms of elements in B. That is it, right. So this T is very well known to me. So first I hit it with a T, and as I said, when we keep operating more and more, you keep accumulating more and more things on the left, right. That is a shortcut to remember, not a very technically precise way, but you understand what I am saying here, right. You hit it with a T, you get an element, then you hit it with another operation. So that second operation is basically another operation that we are well aware of, which is this A in terms of the B. That is the matrix representation of the linear operator in terms of the known basis, not the new basis, the old basis. And finally, as I go along this path, I have to hit it with a T inverse. So this is a T inverse, right. Quite straightforward to see this once this has been explained in this fashion, isn't it, right. So these commutative diagrams are very handy tools to capture or to depict what is being done here, right. So you see, not only have we described to you as to how a change of basis changes the way the representation of a vector in terms of coordinates looks like, but now we have also shown you that given that you know what a linear maps matrix representation in terms of one particular basis is, you should be immediately able to see how that same linear map can be represented in terms of some other basis, provided you know the relationship that exists between these two bases themselves, which is encapsulated by this T matrix, right. So this is what this story tells us, right. And now you immediately see that this is nothing but that good old similarity transformation that you have seen so very often, right. So we will wind up with this description of this linear maps in the abstract sense, with the idea of what is known as the invariant subspaces. Invariant subspaces, all right. So what are invariant subspaces? Here is the definition. Suppose V is a finite dimensional vector space with a basis, say BV is equal to V1, V2 dot 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 till Vn, and S is a subspace of V with a basis. So this obviously this choice of basis is arbitrary, so I can choose any basis to meet this criteria, right. And let us say this is a not just a basis, an ordered basis, okay. So I am not writing it, okay, let me write it, ordered basis. So this is an ordered basis, this is also an ordered basis, V1, V2. So you pick up the first k elements, okay, right. Okay. So what does this mean? What exactly will this do? Right. So if now I want to represent a vector in S subject to this. So, this is let us say the basis for S. Okay. So, suppose you have a representation for S belonging to the subspace S, we have S is equal to summation alpha I V I till I going from 1 through k. Very importantly, plus 0 times V I going from k plus 1 to n, right. So, therefore, any vector S in the subspace S can be represented as a member of the parent space V in terms of coordinates as alpha 1, alpha 2 dot 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 till alpha k, and then the rest are all going to be zeros, right. So, the point is, if you have S which is a subspace of this vector space V, all right, if you have S which is a subspace of the vector space V, then it can be captured and particularly defined in this fashion, where the first k elements out of the n form a basis for S, the subspace, then every element in S, yeah, it is a k dimensional subspace of the n dimensional vector space V, right. So, any element in S given this kind of a choice of ordered basis for the two vector space and its subspace can be represented in this fashion, right, where only the first k elements will be non-zero at most, while the last n minus k elements will be 0 in the coordinate representation. So, this is actually this is basically going to be f to the n, yeah, not in V, but this coordinate representation of the element in V, yeah. So, what is so, I wonder what is so interesting about this sort of a coordinate system, right. What can we say about this sort of a coordinate system? Now, suppose for instance, consider a linear map A such that this A's representation in terms of this basis from f to the n to f to the n. So, remember this A is basically a mapping from a linear map from V to itself, such that you have this mapping, this is the corresponding matrix representation, such that this matrix can be partitioned. Partitioned as A BV is equal to A11, A12, A21, A22. This is now clearly a matrix n cross n, where A11 is of size k cross k, A12 is of size k cross n minus k, A21 is of size n minus k cross k, and A22 is of size n minus k cross n minus k, right. Suppose you have partitioned this in this fashion, all right. So, just to recapitulate quickly, what are the steps? First we had a vector space, then we have its subspace, all right. So, we have its subspace S, okay, such that for a particular choice of the basis for this vector space V, an ordered basis, the first k elements of this basis will also happen to be an ordered basis for the subspace S, And then we see that the coordinate representation in terms of these two choices of ordered basis for V and S yield the representation of any vector S in terms of BV as this, right, which is an n tuple, where the last n minus k entries of this n tuple are going to be 0. We have seen why that is so, because of these zeros here, right. Ordered basis, very important. Again, every time you have coordinates, it has got to be an ordered basis, right. Now, suppose A acts on S belonging to S. So, in general A can act on, so remember this is basically my V and this is also my V. So, it is a mapping from V to V, that is what A is, but within this V somewhere, sitting somewhere is the subspace S, yeah, and here also I can draw that same subspace S. Okay. The point is, I want to study the effect of this linear operator on elements within this subspace S rather than all the elements in the vector space V. Okay. And we will get to the definition of some sort of this invariant subspace in a bit, but for now just focus on what we are trying to do. We are saying that instead of studying the effect of the operator A on any arbitrary element in the vector space V, we will be trying to study the effect of this operator A on elements within the subspace S of V. And we have seen what the coordinate representation of elements in V or elements in S are like. Elements in V would be any arbitrary n tuple, but out of which elements in S are these special n tuples whose last n minus k entries are 0. Yeah? Okay. So, now that we are in the domain of matrices, how do we represent this? So, you take this AS and you represent this in terms of the basis that we have chosen. Okay. What is that going to be like? It turns out that is just going to be nothing but this A in terms of this BV and this S in terms of the same basis BV. Why is this true? Just think about it. Just think about it. What is this saying? It is saying that whether you first take an arbitrary element in the vector space or the subspace S, hit it with this operator and then represent it in terms of this coordinate system, or you take the individual element represented in the coordinate system, again this has got to do with this commutative diagram, the first part of this commutative diagram here, right. Yeah. So, what this is saying is essentially that whether you take this element here, let me use a different color here, what color can I use? Let us see, let me use this color here, okay. Sorry about that. Okay, yeah, here it is, here goes. So, the left hand side, what you see here is this A hit by, I mean this element here, this part of the operation. So, first you hit it with the linear map in the abstract vector space and then you represent it in terms of the coordinate. Yeah. So, that is the left hand side from this figure here, that is what this part of the commutative diagram is, and on the right hand side you have, maybe I will use some other color, yeah, plenty of colors to choose from, right. On the right hand side what you have is, look, ultimately you start from here and you end up here, how it does not matter. On the right hand side what you have is this. What is this? You first take this fellow in this vector space V, represent it in terms of the coordinates and then hit it with the corresponding matrix equivalent in terms of the basis that you have chosen. Yeah. So, this is basically saying that same thing that I have drawn in that commutative diagram here. Here what am I doing? I am first taking this S, of course this S belongs to V as well because it is contained in the subspace S of V, right. So, first I represent it in terms of the basis and then I hit it with the matrix and I end up in Fn. So, I start from V, I end in Fn. On the right hand side, what do? I first hit it with the linear map in the abstract vector space, then I have got it back in the abstract vector space itself because it is a linear operator, and then I represent it in terms of the coordinates through this basis. So, because of the commutative diagram, again this is going to be true. So, I hope that this much you are at least convinced about, right. Okay, good. So, now that we have convinced ourselves that this is going to be true, what does that lead us to? Excuse me. So, now let us look at this part of the operation. Okay. We know that this looks like A11, A12, A21, A22. What is the representation of S? You know that it looks like alpha 1, alpha 2 dot 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 till alpha k, and the rest are all zeros. So, this is of size n minus k, alright. So, what is this going to be like? If I now write down A11, A21 as the first k columns of A, the matrix A, that is, all right, then is it not apparent that this belongs to the image of A11, A21? Let me explain that. When you hit a matrix, forget about the abstract vector space, now think of a matrix and an n tuple, right. You have a matrix, you hit it on the right with a vector. What are you essentially doing? If you do not sort of see this immediately, let us just take this example 1, 2, 3, 4, 5, 6, 7, 8, 9, and you take this to be C1, C2, C3. So, is not this the same as writing C1 times the first column, this is 1, 2, 1, 2, 3, plus C2 times the second column, which is 4, 5, 6, plus C3 times the third column, which is 7, 8, 9. So, it turns out that when you are hitting a matrix with a vector on the right hand side, an n tuple, you are basically taking a linear combination of the columns of the matrix. By the same token, what is this fellow doing here? See, the last n minus k entries are going to be zeros. So, this operation, I put it to you, is basically going to do nothing but take a linear combination of the first k columns of this matrix that is partitioned in this fashion. And if we look at the first k columns, then indeed these are nothing but the first k columns, no, right. So, these first k columns constitute a n cross k matrix. So, this belongs to F n cross k, and of course, this is an n cross k matrix. So, there is inherently an image of this matrix that is well defined, right. Image of this matrix means the set of all vectors which can be expressed as a linear combination of the columns of that matrix. Think of the way we define the image of a linear map. What is the image of a linear map? It is the collection of all those vectors which can be represented as the linear map acting on some vector in the domain. So, all the collection of those vectors in the codomain which have a pre-image, yeah, right. So, that is, those are image maps. So, what is this basically then going to be like? Yeah. So, when you think of the linear map as a matrix, then it is a collection of all those vectors, yeah, which can be written as a linear combination of the first k columns of this matrix. Now, the first k columns of this matrix are always captured if you let just the first k tuple out of this n tuple to be non-zero, yeah, and the remaining you just consider them to be zero weights. So, therefore, this is true then, right. So, this was just an example, let me draw a line around it. This was just for illustrative purposes, yeah. So, we just push ahead with this. So, now you see that when we represent it in this fashion, this AS represented in terms of the coordinates is going to be a vector that belongs to the image of this. And now we introduce this notion of an invariant subspace. So, suppose for a subspace S of the vector space V, which are both finite dimensional vector spaces, we have that for all S belonging to S, AS also belongs to S, which means that, look, if you are taking an element in the subspace S and hitting it with A, it will definitely map it to some element in V, because after all S is contained in V and it maps this operator, or this linear operator maps elements in V to the elements in itself, that is V itself. But the special case arises when, if you find a smaller subspace such that when A is restricted to act only on elements within this subspace, it does not leave the subspace. That is, whatever you get as a mapped vector within V, that is also contained within S. So, in terms of this figure, we are now asking if A is such a linear operator that whenever it plucks out elements from this subspace S, does it necessarily map it to another element, or maybe even the same element within the subspace S itself, not just anywhere outside here, yeah, but only within this subspace itself. Then that is called an A invariant subspace. Then S is an A invariant subspace. All right. So, what is the beauty of this A invariant subspace? Now, if you look at it in terms of matrices, in terms of this representation in Fn, what does it look like? Look, pick out any element in S represented in Fn as alpha 1 dot 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 till alpha k, and then the remaining all zeros. Yeah, this is a coordinate representation in terms of BV. Okay. Let A in terms of the BV act on it. We get, let us say, some S bar is equal to this A acting on this any element. So, this is basically S in terms of PV is equal to this. S in terms of BV. So, we get this, and this now belongs to the image of A11 and A21. Yeah. So, now if S is A invariant, we require S bar, which is basically the image of S, image of the small s that is you picked up from the subspace S. Yeah. So, S bar is basically the image. So, this fellow, this linear map A took an element small s in the subspace S, mapped it to S bar, small s bar in the subspace S back itself. Yeah. That is the definition of invariance. So, if this is indeed left it invariant here, we require S bar to belong to S as well, but that means that the coordinate representation of S bar in terms of BV must also be some beta 1, beta 2 till beta k, and the last few should be zeros, because if S bar belongs to S, then its coordinate representation must not require anything beyond just the basis vectors or the elements in the basis set of S itself, and those are exactly the first k elements in the basis for V. So, you do not require these other fellows, no. these other fellows are going to be zeros. But then from on the one hand we see that it must belong to this, and on the other hand we see that it must be of this form. Putting these two pieces in the puzzle together, yeah, what do we conclude? Putting these two together, I again invoke this, that these require that A21 must be the 0 matrix belonging to, again, what is the size of 2 1? It is probably n minus k cross k. Yeah. So basically what I am saying is, the matrix representation of an invariant operation, okay. Suppose you have a vector space V, a subspace therein which can be constituted or as the span of the first k elements in that basis of V, right. Then if you claim that that particular subspace is invariant to a linear map, then the matrix representation of that linear map must look something like A11, A21, 0, A22, right. That is what the big claim is. So, you see this idea of an invariant subspace, which is a pretty abstract notion in terms of abstract vector spaces. The moment you bring it down to finite dimensional vector spaces and assign some ordered basis and thereafter a coordinate, you immediately see what this matrix is going to look like corresponding to that, such a linear map, yeah, right. So, this is essentially the idea that I wanted to discuss about invariant maps or invariant subspaces and the representation of the linear map when you have chosen the basis carefully for that invariant subspace, okay. Right. So, this is where we will now, for now at least, we will draw the line on this invariant subspace and this abstract vector spaces. And now that we have hopefully thoroughly established the close ties between linear maps or linear operators in finite dimensional vector spaces and matrices, n cross n matrices that are operators, yeah. We shall hereafter now no longer be emphasizing at every point about the importance of studying matrices, but take it that you have already grasped the importance of matrices to our particular study, right. So, now we shall start talking about matrices, and hereafter I shall drop this box bracket representation, and when I write A, please take it to mean matrices rather than the abstract linear map over the vector space V. We will always assume that for the vector space there is a finite dimensional vector space, there is a finite basis, there is a coordinate assignment, and therefore there is a matrix representation of the linear map, okay. So, now we are going to talk about some special maps and some special invariant subspaces with respect to matrices. One of the first things that you encounter when you talk about square matrices is the eigenvalues and eigenvectors, okay. So, how are they defined? Very, not putting it in a very rigorous fashion, but if you have A, so suppose you have a matrix A which is a complex matrix n cross n, yeah, n columns and n rows, then if you have A V is equal to lambda V, where V is an n tuple of complex numbers, lambda is a complex number, right, then this, yeah, is basically going to be, of course, you might say that if you put V is equal to 0, then this is trivially true, right, but that does not lead to anything, right. So, V has to be non-zero in this, yeah. So, then such a pair, so then this lambda and this V is an, anything that satisfies this equation, any lambda and V pair, okay, is an eigenvalue eigenvector pair for the matrix A. All right. So, what is its connection to this idea of invariant subspaces that we have spent so much time studying thus far? Yeah. Let us quickly take a look. Now, suppose we have AV is equal to lambda V. I am sure you have already studied eigenvalue eigenvector problems in great detail. What is the way to evaluate? Of course, you do not necessarily, saying it for the sake of abstract concepts is good, but you do not really solve for eigenvalues and eigenvectors in this fashion through trial and error, right. We all know that in order to solve for eigenvalues, what you do is you equate determinant of A minus lambda I is equal to 0, and this turns out to be a so called monic polynomial. This is what we call as the characteristic polynomial of A, yeah, and this we equate to 0. So, this is the characteristic polynomial. When you equate this to 0, you get the characteristic equation. So, chi A lambda is equal to 0. This is the characteristic equation for the matrix A. All right. So, obviously, this will look something like lambda to the power n. It is a monic polynomial, which means that the coefficient of the highest degree in the polynomial is going to be unity. Yeah, this is going to be lambda n, then this is going to be a n minus 1, lambda to the n minus 1, so on and so forth till you get a 0 is equal to 0, right. Of course, you can also write this as lambda minus lambda 1, lambda minus lambda 2 dot 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 till lambda minus lambda n is equal to 0, where lambda I and lambda j need not be distinct, but of course, by the fundamental theorem of algebra, if it is an nth degree polynomial and if you equate it to 0 and want to find its roots, then there will be exactly n roots over the complex field, right. So, then these lambda 1, lambda 2 dot 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 to lambda n not necessarily distinct are the eigenvalues of A. So, this is the way we find the eigenvalue, okay, right. Great. So, we have familiarized ourselves with this idea of this equating this determinant, getting this monic polynomial, equating it to 0 and getting the characteristic equation. If you can solve for it, you will get all your eigenvalues repeated or otherwise, all right. The point is, having obtained these eigenvalues, we can now define the so called subspace Ek as kernel of lambda k I minus A, okay. So, this is a subspace. Why is this a subspace? Because any kernel of a matrix is a subspace, okay. So, define this. So, we define this Ek, this kernel of lambda k minus A, to be a subspace, and the claim is that this Ek is A invariant. How do we prove this? Yeah. So, for that you have to take any arbitrary vector that belongs to this subspace and see that if you hit it with A, does it also belong to the subspace, right. So, let us see. Suppose V belongs to Ek. This means that lambda k I minus A times V is equal to 0, right. Anything that belongs to the kernel or the null space of this matrix, kernel of the operator, null space of this matrix, same thing, yeah, right null space, yeah, it is going to be 0. Now, what does that mean? What can we deduce from this step? Yeah. So, from this step we see that it means lambda kV is equal to AV. In other words, this V will then turn out to be an eigenvector corresponding to the eigenvalue lambda k. But now take AV instead. Yeah. What do we need then need to show? We then need to show that if V belongs to Ek, does AV also belong to Ek? So then the question we ask is, does AV belong to Ek? If the answer is a yes, then Ek is A invariant by definition. If the answer is no, then Ek is not A invariant. Simple enough, right? Pretty straightforward. So then we see that let us hit AV or candidate that we want to check with the same excuse me, lambda ki minus A on the left. What do we then get? We get that this is AI minus A squared times V. Now because we can now pull this out, we can just pull out the A from the left. So this is the push pop. So we push this A in from this side and we pull this A out or pop this out from this side. So this is a push pop technique. Sorry, I missed the lambda k here, right? So then this is lambda ki minus A times V. And now I am just going to forget about this A here and I am just going to focus on this other part of the term that remains. That is this. What is this? This I already know devolves to 0 because of the fact that originally this V to start with belongs to Ek. So this is just going to be A times 0, right, and therefore this is going to be 0. That means that AV belongs to Ek as per my check, right. So if AV belongs to Ek, because remember this AV when it was hit by lambda k minus A, it got pulverized. So therefore this satisfies the condition for belonging to the kernel of this and therefore it belongs to Ek. If it belongs to Ek, then what do I know? I had V which belonged to Ek and now I hit this V with this linear operator, this matrix A, and still it belonged to Ek. Therefore Ek is clearly A invariant. So the moment I define this invariant subspaces in terms of these abstract vector spaces, I had this motivation that I wanted to get to some interpretation of this invariant subspace when we have matrices, and immediately as soon as we landed up with matrices and this eigenvalue eigenvector problem, we see that we encounter one such A invariant subspace, that is the kernel of lambda k minus A, where lambda k happens to be an eigenvector of the matrix A. Lambda k happens to be an eigenvalue of the matrix A, right. So now the next claim, and this is the last thing we shall see in today's lecture before we wind up, is that we will keep this result for the moment in our kitty. We will revisit this when again after we have had a brief discussion on Jordan canonical form maybe in the next lecture. But in this lecture, before that I want to just give you a glimpse into one very important result. This is a sort of a sufficient condition for diagonalizability of a matrix, okay, using a similarity transformation. You are probably already aware of it, but it is not necessary, but it is sufficient. So suppose A has n distinct eigenvalues in C, then A is diagonalizable through a similarity transformation. Now read very carefully in between these lines. and try to translate them back into linear maps, in the language of linear maps. If I am talking about similarity transformation, immediately in the language of linear maps, that translates to what exactly? It turns out it translates to a change of basis. So, what I am saying is that I can make this linear map look nice as a matrix. When I say nice, I mean a diagonal form is a nice form, isn't it? So, I can give it a nice look, provided all the eigenvalues are distinct. Of course, that is a, as I said, sufficient condition, not necessary. Even if the eigenvalues are not distinct, I might be able to diagonalize such a matrix. Okay? So, let us see what is the basis for this, or what is not the basis, not as in a technical basis, what is the foundation or what is the logic or reason behind this claim? Yeah, what makes this claim work? Look, if you have distinct eigenvalues, then you have a v1 is equal to lambda 1 v1 dot 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 till a vn is equal to lambda n vn. Yeah. Now, if I write them side by side down like this, then I have a v1 v2 dot 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 till vn. Yeah, and this can now be written as v1 v2 dot 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 till vn, and I have this representation dot 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 till lambda n. I urge you to check this, okay, that this can be written. So, each of these v's, vi's, they belong to complex n tuples. Lambda I is a complex number. A can also be allowed to be a complex matrix, right. So, of course, we are diagonalizing over the complex field. So, there are no restrictions here. You can have complex eigenvalues also, right, provided the eigenvectors are also allowed to be complex n tuples, right. Now, let us call this as T. The only thing that now prevents us from writing T inverse A T is equal to lambda, which is basically nothing but this lambda 1, lambda 2 till lambda n, is the fact that we have not established that this matrix T is invertible, or in other words, the matrix comprising eigenvectors corresponding to distinct eigenvalues, n distinct eigenvalues, is going to be always invertible. Yeah, we have not proved that. So, that is the one thing that I am going to prove today and conclude this lecture, maybe not very rigorously again, but you will hopefully get the idea, right. And if there are any gaps in the proof, I urge you to take it as an exercise to fill in those gaps. So, what am I saying here? I am saying that this matrix T that I have defined here is going to be invertible. Why am I saying it is going to be invertible? That means I am also claiming that these vectors v1 through vn are going to be linearly independent. So, suppose not, suppose v1 v2 dot 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 till vn is not a linearly independent set, then, okay, let me write it as a new sentence, then for C1 V1 plus C2 V2 plus dot 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 till Cn Vn is equal to 0, there exists some Ci such that Ci is not equal to 0. Of course, if all the Ci's have to be equal to 0 whenever this summation or this linear combination of these vectors is 0, that is the specific definition of linear independence. So, if you are saying that they are not linearly independent, and in other words implying that this matrix T is not invertible, then it must be that at least one of these Ci's from C1 through Cn must be non-zero. Okay. Let us say without loss of generality that this Ci is non-zero. Now, consider A minus lambda 1 I, A minus lambda 2 I dot 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 till A minus lambda I minus 1 I, and then you omit this term A minus lambda I plus 1 I dot 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 till you go till A minus lambda n I. So, the only term I am deliberately omitting from this is the one term for which suppose I have this Ci is equal to non-zero. If it were all 0, again I have nothing to prove. The only way this can be disproved is that this T is non-invertible is if one of these C's happen to be non-zero, right? Because if this is a linearly dependent set, then this matrix will not be non-singular and therefore inversion is not possible. But now if that has to be so, then I hit this C1 V1 plus C2 V2 plus dot 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 till Cn Vn, and on the right hand side of course it is going to be 0, right. So on the left hand side and the right hand side I am hitting with this term, this particular operator on both sides. So if I hit 0 on the right hand side with this operator, it is still going to lead to 0, yeah. But on the left hand side if I hit with this operator, what do I get? For k not equal to I, consider a minus lambda 1 I, a minus lambda 2 I dot 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 till a minus lambda I minus 1 I, a minus lambda I plus 1 I dot 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 till a minus lambda n I times Ck Vk, which is nothing but I can now pull out the Ck on the left hand side, it is just a scalar, right. So Ck, what happens when I operate this with this a Vk, so this Vk can be pushed in. So this is a Vk minus lambda n Vk. What is a Vk? So this is going to be a minus lambda 1 I dot 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 till last term is a Vk minus lambda n Vk, okay. What is that going to be equal to? This is going to be Ck a minus lambda 1 I times dot dot dot, a Vk is nothing but lambda k Vk minus lambda n Vk. Now I am going to pull this out. So Ck times lambda n minus lambda k minus lambda n times a minus lambda 1 I dot dot dot. Remember there is this one term missing, that is a minus lambda I. And now I have the next term to deal with, which is lambda n minus 1 I times Vk, yeah. Again I do the same operation, and likewise I want you to see, fill in the blanks here for me, that Ck times this will eventually lead to lambda 1 minus lambda k minus lambda 1, lambda k minus lambda 2 dot 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 till lambda k minus lambda I minus 1 dot 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 till lambda k minus lambda I plus 1, and then this lambda k minus lambda n, yeah. What can I say about this? Yeah, eventually at some point if k is not equal to I, one of these terms is definitely equal to 0, somewhere there is a term like lambda k minus lambda k, right. So that itself makes this vanish. So if k is not equal to I, then I have this eventually vanishing. On the other hand, if k is equal to I, then you see that this term turns out to be Ci times lambda I minus lambda 1, lambda I minus lambda 2 dot 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 till lambda I minus lambda I minus 1, then lambda I minus lambda I plus 1 dot 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 till lambda I minus lambda n. Look, because the eigenvalues are distinct, each one of these terms is not equal to 0. So all of these terms are not equal to 0. So then going back to this original expression, please fill in the blanks for me, okay. What I get from this original expression here, I can now bring it down all the way here to conclude that once I have hit it with this operation, I get that Ci times this whole non-zero element is the only term that survives. Remember the other terms for k not equal to I, they have vanished. So this is going to be equal to 0. So Ci times some non-zero is equal to 0, therefore that leads to the only conclusion that Ci must be equal to 0, but I started with the assumption that Ci happens to be the only term, at least one term which is not equal to 0. So any term that I assume to be equal to non-zero and thereby try to prove that this is a linearly dependent set eventually is contradicted, and it turns out that that term must be equal to 0. This means that this is true if and only if Ci is equal to 0 for all I, implying that this set of vectors, eigenvectors corresponding to distinct eigenvalues, is always going to be linearly independent, right. And because it is going to be linearly independent, this is a full square matrix, n columns, it is going to be invertible. Therefore, I have that T inverse A T is indeed equal to a diagonal matrix, and therefore, this is diagonalizable. Okay. So, in the next lecture we shall start talking more about the more general form, which is the Jordan form, and see how this diagonal form is a special case of that. Till then, take care.